Right, guys, today we are continuing with our matrices. I hope you remember what we did yesterday. Let me just get a good pen there. Right, it's matrices again. Just recapping a bit what we did yesterday, I think we agreed that at the end of the day, after the introduction, a matrix looked more or less like a rectangle of numbers, and there are different types named by rows and columns, isn't it? Like, for example, let's get A here, which is 2, 2, 1, 3, minus 4, 1. That's a rectangular matrix. But if you've got one matrix like this, actually these brackets, you can use them in different. You can use this one, so that one is not a problem. Let's say here 1, 1, 3, 2, minus 1, 4, 3, 3, 1. That. Then we call that matrix a square matrix. Are we together? Now, what I want to do now, I just want to highlight some aspects of matrices which are very important before we can continue with other things. Now, when we have a matrix like this, an entry, remember we said these things are called entry. An entry like this is an entry which you can call E1, 1. What am I saying there? I'm saying that entry is in row 1 and the column 1. Are we together? That's important. Then we've got this. We've got these entries here. I'm trying to put them in between lines there. And then there's 1, 3, 4 and the 2, 3, 3. That entry, those entries there, they form what we call the principal diagonal. We didn't talk about that yesterday, did we? No. No. That's the principal diagonal. And the other diagonal, which is this one, we call it the secondary diagonal. Secondary. Is that right? Okay. So then, having that, this is how we name the entries: row, column. Then there are matrices like this. Let me write there. A matrix like this. Let's say 4, 0, 0, 0, 3, 0, 0, 0, 1. You can see that that is a 3 by 3 matrix, the square matrix. Now, somewhere here, there, and there, we only have zeros. Then that matrix is called a diagonal matrix. Diagonal matrix. I'm just talking about, when I'm saying diagonal matrix, everybody must understand what I'm talking about. So it means that the entries outside the principal diagonal, in this case, we'll be talking, we are referring basically to square matrices. Square, what's that now? Square matrices. Now notice that we've got square matrices. We can call, let's say, if I want to collect all the square matrices of 2 by 2, I can just say M2. I'm talking about the set of all the matrices of 2 by 2. Then when I'm talking about M3, I'll be talking about the matrices of this nature. Now notice, if I've got matrices of this nature, I add them, I get a matrix of the same nature. I multiply them, I get a matrix of the same nature. Is that right? Yeah. But sometimes you can multiply 3 by 2, you don't get a 3 by 3. You can multiply 3 by 3 by a 3 by 2, you are not going to get a 3 by 3. That's right. But when you're dealing with square matrices, you multiply a square matrix by square matrix, you get the same type of square matrix altogether. Okay, that's that. So that's the diagonal matrix. Then another special matrix which you want to know about is this one. I'm taking an example of a 3 by 3 here. You must imagine an example of a 4 by 4, a 100 by 100, a 2 by 2. A matrix like that. One must say, what's the interest of having a matrix like that? All the entries are 0. It's actually called a 0 matrix. That's a 0 matrix. That's the matrix which actually will behave like 0 when you're dealing with numbers. What happens when you're dealing with 0 to numbers? You say 2 plus 0 is equal to 0 plus 2 and still equals to 2, isn't it? So any matrix added to a 0 matrix, of course, you cannot add a 2 by 2 matrix to a 3 by 3 0 matrix. If you are adding a 0 matrix, but it must be of the same type with the matrix you are dealing with, isn't it? Then you get the same matrix. So we will say now if A is a matrix, whatever order, plus a 0 matrix of the same order, we will still get here A. And that is important again. With numbers, we know that A plus B is equal to B plus A. In matrices also, matrix A plus B is equal to B plus A. Now we are saying the addition is commutative, subtraction is also commutative. But what is not true with matrices, if you multiply A by B, you don't normally expect to get the same thing as B by A. Because remember, yesterday we saw that there are some cases in which you can multiply matrices in one order, but in the other order you cannot multiply. Even if you can multiply in two orders, it doesn't necessarily mean that you're going to get the matrix, this being commutative. So multiplication is not commutative. Am I making sense there? Okay. So I hope we also talked about multiplication by number, isn't it? So if you've got to multiplication, let's say we've got that, you know what that is. Now you multiply all the entries by that. But if you also have got A by B by C, then you've got to do this as a binary operation, then do that. Then this is equal to the same thing as multiplying A by B, binary there, then by C, binary between these two. So what I'm saying that multiplication of matrices is also associated in this. At the moment, I'm not going to talk about division of matrices because there's not terminology like that, dividing by matrices. But you will see that there is some kind of equivalent operation or some kind of operation which resembles division, but let's not talk about that now. Are we together, guys? Now, I think we're now in a position to continue with our work. I think this is enough for recapping what we did yesterday. Let's see what we can do for today. So everybody knows what is the there's one matrix which I didn't mention here. Let me just quickly do that before I go very far. This is a very special matrix. I mentioned the 0 matrix. Now I need to mention this one. I'll just say IN. Then let me take I3. And then let's say 1, 0, 0. 0, 1, 0, 0, 0, 1. And that is called identity matrix. That is the matrix which when you multiply, let's say you're just dealing with any matrix A, we multiply A by I, will definitely get I by A, which is same thing as A. Now, when you multiply any other matrix by the matrix, it just behaves like as 1. Let's say number A multiplied by 1 equals to 1, multiplied by A equals to A. Those are properties of numbers, and they are extended to the properties of matrices. Are we together? Okay, that's very important. We're going to deal with that. Now, remember, do you remember yesterday how I introduced matrices? Do you remember? Can you remember how I introduced matrices yesterday? What did you see? Before I talked about matrix, I think you saw a system of equations, isn't it? This is what we saw. It was 2x plus 3y. It might be not exactly the same system, but you might remember that it was more or less something like this. Let's say maybe 8 there. That's a system of equations. I think that already motivates, should generate some kind of a question. What a matrix that has got something to do with the systems of equations. That's right. They are. If you look at this system, this system of equations, I can, like what I said yesterday, I said we can isolate coefficients here and say 2, 3, 1, 5, and they do that. We did multiplication of matrices yesterday. This matrix is 2 by 2. But we said another matrix which you can have a matrix of these unknowns, which is actually x and y. Now, if you look at the right-hand side of this system, it's actually a result of multiplying two matrices, this one and that one. Is that right? You see that? Remember we said we push this thing up, we multiply and add. So this is actually a result of multiplying matrices. Then this is equals to, then we say this is 7, 8, and that. Now, if I call this matrix B, and I call this matrix X, and I call this matrix A, you see, now what have I done there? I have actually got A multiplied by X equals to B. Something which is similar to what I had at school, which is 2x equals 8, and 8 is similar to B. Independent side. How do you do that? Now, once I've done this kind of situation, like this and that, this is a particular thing of this one, symbolically. So this, what I can say here, this is what we can call the matricial or the matrix form. Let me say use the word matrix form. The matrix form of representing a system of equations. In other words, something which was as cumbersome as this, I just represent it simple, like 2 times 8. So I'd say A times that is equal to 2B. We understand now? So at the end of the day, I should be able to give you a system of equations and say, guys, transform this system of equations into matricial form. You must know what to do. Are we together? Okay. Let's see whether you know what to do. Let's take this one. Let's take this example. We've got x plus 3y plus 3z equals to minus 3. Then I've got 2x plus 2y plus z equals to minus 5. Then I've got 4z minus 2x minus y equals to 6. Let's talk about this. Focus on this. When I'm here, this matrix here, I call it the matrix of the coefficients. Altogether. Now, when you come here, you want to represent this thing this way. You must first of all focus on your matrix of the coefficients, isn't it? The matrix of the unknown is very easy. The matrix of the right-hand side is very easy, you can see it. But you must focus on the matrix of the coefficients. Who wants to attempt to give me the matrix C there? I'll use C now for the matrix of the coefficients. Who wants to tell me? Come again? Can I have one person who wants to talk? 1, 3, 3. 1, 3, 3. I think you can see it's going raw. Is it? Okay, next. 2, 2, 1. 4 minus 2. That's what I was checking. Are people sleeping? No. This is exactly why I put this thing here. I wanted to show you a porthole. There's a porthole here. You must be careful. Before you decide on the matrix of coefficients, the first thing to do is that you must check whether all your variables in all the equations are in order. It doesn't matter that you can start with Z here and then X is here and Y is here, but they must be consistently in order. Are we together, my friend? Good. I hope you thank yourself for making that mistake. Now you know what to look after. Is that right? Yeah. Right. Let's see. So in this case, what we'll do, we would rewrite this equation. Maybe in the next step between this and that, we can rewrite this equation and make sure that this. Are we together? Maybe let's rewrite it. Since we've got technology which is fast here, we can just say. Then, what was the coefficient? Minus what? Minus 2x minus y plus 4z. Then now this will come as minus 2 minus y. Oh, sorry, not 2, 1. The coefficient, isn't it? Yeah, okay. Then minus 1, eh? Then 4. All together. So somewhere there, I should put an exclamation mark. Look up. You must put the look up. Are your variables in order? All together. This solution will not change if we take the whole column and put it there, or we swap it around, or we multiply the equation by a non-zero coefficient. The solution x, y, z will be still the same. So now the x part of it, the unknowns, would be x, y, and z. And then the independent terms, the p's, will be what? Minus 3, minus 5, 6. Is that right? Then we've got C, x equals to B. That's that system in matrix form. Are we together, guys? Are we there? Okay. So now, already we have seen this very, very close relationship between matrices and system of equations, isn't it? Are we together? We can actually use matrices to represent the system of equations. So now, I think what will be interesting now is the system of equations, we solve them. Now, if we've got them in this situation, how do we solve them? That should be interesting, isn't it? Okay. So let's see. Now, I think before we can talk about solving systems of equation using matrices, I think let's talk about something else which concerns matrices, determinants of matrices. Now, the question is, what is a determinant? If we're going to talk about determinant. A determinant is a number which you assign to a matrix. Let's say we've got a matrix here A. We can take this A, assign it a number, like a real number. It can be negative, positive, can be 0. And that number, we denote it by det of A. It's kind of a function. In this case, we're talking about square matrices. You take a square matrix, you assign the number, we call it determinant of matrix, or sometimes we use this notation. You take that A bar, a notation which is more or less like absolute value. But don't confuse that this means that the number is positive. It's just a number. It can be positive, negative, or it can be even 0. Right, let's pause there for. So now what is interesting is that what is now interesting is that if we are given a matrix, what do we really do to get that number? Or what kind of a computation do we do to get that number? Now, let's say we're given a matrix A, which is, I'll take a simple matrix here, like 2, 1, 3, and 4. That's a matrix. Now look at these two things. This is very, very important. Do you see the lines I'm using there? Sorry? Can you listen to me? Do you see the lines I'm using there? Do you see the brackets I'm using there? Those are two different things. So don't use these lines when you want to mean this, or you use these lines to mean that. Are we together? Okay. So now, what do we want now? We want the determinant of A. I'm going to use this thing, and I might use this notation or use that notation, doesn't matter. Are we together? Now, how do you then compute the determinant of A? What are you going to use? You are actually going to use the entries of A to calculate that number. How to use it here? Now, what are you going to use here? You're going to say A11 multiplied by A22 minus A21 multiplied by A12. Do you see what I'm saying there? I'm saying we're going to take this, the product of the principal diagonal, the product of those entries, minus the product on the secondary diagonal. So in this case here, this is going to be equals to 2 by 4 minus 3 by 1, which is simple 8 minus what? 3, and then our determinant is 5. Are we together, guys? That is very important. Yeah, this is something to know how to do. You must know that a determinant is a number which you assign to a matrix, and then you must know how to assign that number. What kind of calculation you must do to assign that number. Are we together? The question can come in any form, but whenever the word determinant is mentioned, this calculation for a 2 by 2 matrix cannot be overlooked. It must actually come up in your head that, okay, if I'm talking about determinant here, something like this must happen. Are we together? Okay, that is a 2 by 2. Now, this one looks very, very easy, simple, and straightforward. But there are many, when you get to matrices of 3 by 3, which I'm going to do an example now, you find that there are many ways of approaching that. So I think let's quickly then look at a 3 by 3. For me, that is important to look at now. So I want to keep that there. We're talking there about what? Determinant. Just opening space there. Now let's talk about the 3 by 3 matrix. let's say we've got an A which is equal to 1, 3, 3, 2, 2, 1, minus 2, minus 1, and the 4. That's a matrix. Now, I've talked about the 2 by 2. Now I'm talking about the 3 by 3. That's right. And then let's focus on it. 2 by 2 is almost like, I don't know what to say. Because sometimes use the word simple. It's meaningless depending who you are talking to. Like that guy there who is just coming in just now. I said, no, 2 by 2 is simple. He said, simple, what do I talk about? Altogether. So then, maybe it's straightforward, but again, when you say straightforward for that person, what are we talking about? Altogether. So I'm not going to say it's simple. What? Let's say like each problem there's got its own kind of challenge, isn't it? But we saw that when we're talking about 2 by 2, what exactly are we supposed to do? Altogether. Now let's see what we're going to do when we're talking about 3 by 3. Let's say A. Want the determinant now. Look what I'm doing now. I'm writing 1, 3, 3, 2, 2, 1, minus 2, minus 1, 4. Then that. I'm going to sound like a fool here, repeating myself several times. I don't mind sounding like a fool, as long as I know what I'm doing. Look at what I've done here. I've written this symbol here. Look at the difference between these two. If you don't make the difference, then you have something wrong there. So when I'm writing like this, I'm not talking about the matrix here. I'm talking about the number which is assigned to that matrix. Altogether, which is determinant. So now I want to show you how am I going to calculate this. Listen, I'm not asking you, do you understand? I'm showing you. You don't need to understand. You need to see how it starts. Altogether. Because there's confusion. Sometimes people confuse seeing and understanding. You must see how it's done. And then maybe there are some things you are going to understand from how it's done. But now see how it's done. Altogether. This is what I'm going to do. Then this is what I'm going to do. I'm going to get that product. How many factors am I having in that product? 3. I'm then going to get that product. But that product is 2, isn't it? But I need 3 that refers to the other one, isn't it? Then that product, I'm going to go and borrow this guy from this side. So how many do I have now? 3, isn't it? Then I'll come and say, I want that product. But that product, I've got a problem there. I've got only 1, isn't it? But I need 3 like the others, isn't it? Then I think now everybody knows that then I'll borrow on the other side of the principal diagonal and I'll get these 2 guys there. Altogether, what are my products? 1, 2, 3. 1, 2, 3, isn't it? So I started from the principal diagonal and went up. Another guy from Japan, he can start from the principal diagonal and going down. But if he respects the rule of taking 3 factors, he's going to get the same thing. Altogether. Okay. So what's going to happen there? This is going to be 1. Sorry, let's write in black. Black is beautiful. 1 times 2 times 4. I'm talking about the product number 1. Isn't it? 1 times 2 times 4. Plus 3 times 1 times minus 2. Then I write 3 times 1 times minus 2. Do you see why I'm putting my brackets there? I don't want to cause confusion. Plus 3 times 2 times minus 1. Then I'm done on that kind of parallel. Then I say minus big bracket there. What am I going to do now? I'm going to do the secondary parallels. The secondary parallels are 1, 2, completers. Then 3. You guys, let's be 3. Do you see that? Okay. Then what I'm going to do now is minus 2 by what? By 2 by 3. Everyone can see that, isn't it? Then you go to number 2 plus 3 by 2 by what? By 4. Plus, let's close the bracket there. We'll put the next thing there. What is that? Plus 1 times minus 1 times 1. Then what we need to do? We need to work out this sum, and to work out this sum, then carry out this kind of subtraction. So let's quickly do that. This is 8, guys. If you don't know how to multiply, it's your problem. This is 6, and this is 6 minus 6. This is our that. Then minus small bracket there. What is this? Minus 12. And what is that? What is it? It's 2 times 4, 2 times 4 times 3. That's what? 24. Plus 24. And here it's minus 1. Then it's minus 12 plus 8 minus 13 plus 24. What is left here now? I can give it to a grade 1 and do it. You finish it up. It's minus what here? Here is minus 13. What do I say? Minus 13 plus 24. What is the answer? Minus 11. And here? Minus 4 minus 11, isn't it? Which is 11 minus 4. What is that? 7. So we can now say that determinant of A is equals to 7. All together? What are you saying? Here, it's 11. Or positive 11. Sorry, there's a mistake there. Positive 11, is that right? Then what is this? It's minus 11 minus what? Minus 4. What is that going to be? Minus 15. Okay. So then this is wrong. The answer there is minus 15. Then let's just get rid of this guy here. Sorry. And say determinant of A is equal to minus. What are you saying there? Now please man, don't come up with another accent here. You've got too many accents here coming from Mother's Day and what else. All together guys. That's one way of doing it. That's one way of doing it. So let's keep it here. Let's keep it here and say determinant of A is equal to minus 15. Now, let me quickly show you another approach. I'm not going to advertise of any of these approaches. Ne? You'll choose what you want to do. Yeah, because I'm not like liver brothers who make Omo and Self, then they say Self this, that, and then Omo this and that. I'm not going to advertise anything. I'm not going to advertise anything. Sorry. Sorry for that. Now, what am I going to do now? This is what I'm going to do. I'm going to write 1 bar like that, and then write 1, 3, 3, then write 2, 2, 1, then write minus 2 minus 1, and 4. Then I write another bracket there. Then just for making a kind of a mark for people to see what's happening here, I'm going to like make this matrix a little bit bigger. I'm going to argument 2 things here and say 1, 3, 2, 2, minus what? 2 minus 1. Then what I'm going to do now, let's just choose a beautiful thing here. Then you say diagonal, diagonal, diagonal. We make that product. Then the other way you say diagonal to the second diagonal. You follow, and then that way all your rows which you are going to use are going to be 3, 3, 3, 3, isn't it? So the guys who are going to stay lonely are those guys there and that guy is there, but they are used. This guy is the guy who is used there, isn't it? And then this guy is the guy who is used there, isn't it? So it looks like they're not used, but they are used. Then you start saying, okay, doing exactly the same kind of calculation. What's going to give you there? You're going to have this 2 minus 2, 3 plus minus 1, 1, 1 plus 4, 2, 3. Close. Minus, I'll put it here underneath. What do? No. I did a mistake there. Do you see that? So these are the secondary, isn't it? So which is plus. I can put a minus sign before there, isn't it? Yeah. Then and now take the principals. Actually, the way I did it, I think for organization, I think it's better we start with the principal diagonal, isn't it? I just got carried out there. I mean, it's normal to just get carried out away, but you must be careful not to be carried away. Right. Then you get there 1, 2, 4 plus 3, 1 minus 2 plus 3, 2 minus. Sorry, that's wrong. The way I've written it is not right. I need a bracket there. Bracket minus 1, close that. Then, sorry for the confusion there, but start with this, then subtract that. But otherwise, but anyway, A plus B is equal to B plus A. So then, if you don't get this number, then there's something wrong with one of the things we did. Altogether. But otherwise, this is supposed to give you exactly the same number. That's just another organization of how you can organize your determinants to calculate. Altogether. Okay. So I think I will stop there for a while. We've gone up to determinants. Now we're going to see how we can solve systems of equations using matrices. Thank you for listening.